Boa tarde a todos, satisfação revê-los. Espero que todos estejam bem, com saúde. Espero que nós possamos, em mais um dia, no caso, em mais uma tarde, ter mais um evento importante de aprendizado, de atualização e também de um bate-papo com um profissional que tem uma relação especial com a geotecnia internacional. Espero que todos estejam aptos a aproveitar da melhor forma possível a palestra de hoje, o webinário de hoje. O professor Richard Jardine, ele dispensa apresentações, mas eu passo a palavra para que o professor Márcio Almeida o apresente e que todos possam, então, desfrutar dessa magnífica palestra.
So, thank you, Thiago and Geotecnia Brasil for the invitation. It's a great pleasure to moderate this section with Richard Jardine. Richard is known for most geotechnical people, and he has a good link, long link with Imperial College, and he's a former ranking lecturer, as already mentioned. So it's a great pleasure to have Richard with us tonight, speaking about wind farms and design and new challenges, new findings, and so on. So please, Richard, go ahead with your lecture, with the webinar, please.
Thank you very much, Marcio. So I will move to share my screen in a moment and show you the slides that I've prepared for our talk this evening. So as you'll see from my opening slide, I'm going to be talking this evening about geotechnical research contributions to optimizing offshore wind turbine design. And my talk actually starts off by recognizing that offshore wind is a very expensive way, in principle, of making energy. We need very large plants, and we have to go out into the sea, and this is expensive. In this cost, foundations make up 20 or even sometimes 30% of the capital costs. And so initially, when offshore wind started, it was more expensive than fossil or nuclear fuel as a means of generating electricity. So what has happened is over the last decade or so, multiple efforts have been made to apply an extended oil and gas experience to try and reduce the costs and increase the capabilities of. This has been very successful, and many groups such as ours around the world have contributed to bringing down the cost of individual. And now wind energy, at least in Northern Europe, is about the cheapest way of making electricity. Cheaper than nuclear, it's cheaper than burning coal, it's even comparable to burning gas. Now, the UK has led the way on this in terms of market share. We have the largest capacity installed in the world, about 25% of the total, and that's allowed us to reduce our coal generation massively. And if you've been watching the news from Glasgow with COP26, you'll see this is a major achievement. And the UK, which is almost built on coal, now only uses 1.7%. Its electricity comes from coal, and the plan is to stop this completely within 3 years. And of course, this is very good for the environment. Now, wind turbine foundations really depend principally on the geomaterials and the water depth and the ocean loading and where you are in the world with regard to regulation regime. We have in shallow depths many monopile foundations. As we go into deeper water, we have jacket foundations, miniature oil rigs. And as we go deeper still, we have floating structures. And I believe at the moment the UK has the only operational floating wind farm, but they're likely to become much more common around the world in the years ahead. So for monopiles, we get lateral loading. For jacket piles, they principally work in pull to take the moment supplied by the wind and waves. And in all cases, we're concerned with ultimate conditions and also initial loading response, which governs the cyclic behaviour, and that really depends on the small strain behaviour of the geomaterials present. How can we aid design as geotechnical engineers? Well, come up with new ways of calculating and predicting load displacement and ultimate capacity for offshore wind. We've done this by combining advanced element testing, numerical and physical modelling, and also field monitoring. And keeping in touch with what happens in the field with real wind farms has been very important to exploring the questions that are posed by field observations. So we have multiple challenges, and around the world I've been trying to meet these in Europe and now Asia, USA and elsewhere, hopefully Brazil. So we're going to talk first about monopiles and then move on to floating and finally jacket structures. With monopiles, their operational response is controlled by stiffness and verticality. The wind turbine operators say that you have to have certain parameters met to satisfy design. And this has been done with these low length diameter caissons quite successfully so far in very large wind farms in Northern Europe. What is found, though, is that the field monitoring of the frequency responses of these structures shows that the standard PY methods that have been used to design, for example, offshore platforms for gas, lead to over-design, over-conservative design in the soils we have in Northern Europe. We saw the same thing, actually, with North Sea oil and gas platform piles, and I'll mention that later. So there's scope to do better engineering, better analysis, and so reduce costs and allow monopiles to go into deeper water use and maybe with more challenging geomaterials. Now, our work in this area was partly associated with the PISA project, which was led by Ørsted, the world's largest developer. And we spent about 5 years on this project, PISA 1 and PISA 2. Now, the PISA project was led by industry, but its academic work group, which set the scientific objective, Oxford, Imperial College, and University College Dublin. And our approach was to come up with methods that were tuned to match the monopile length to ratio, which is much smaller than that for conventional offshore oil and gas piles, regional soils that we find in our area and do intensive testing on those, and also to recognize cyclic action. So the key steps were starting off actually with numerical analysis and laboratory research. From there, we proposed an improvement on the PY approach, and then we went to test that with extensive field tests on piles up to 2 meters diameter, UK glacial till site, and a French sand site. So at each of these test sites, we installed 14 piles. They had 3 diameters, so we could look at scale effects, a range of geometries and wall thickness and so on. And we did both static testing to failure, as well as rate and cyclic tests. And we had lots of instruments on the piles and in the ground. We had comprehensive site investigations, including advanced seismic testing and CPTU testing, plus a lot of laboratory experiments too. So this shows you the list of authors involved, many people involved. My name is in there somewhere, but the project was led by Byron Byrne from Oxford, and he and his team particularly organized the field tests. And here you can see the smaller piles and the medium piles and the largest piles that were tested at each site. And here we can see for the largest piles, 2 meter diameter piles, undergoing extensive axial loading with a large moment applied as well. It was actually at our test site in France, which involved sand. Now, the conventional approach, the monopile design, is to use PY curves, which provide only horizontal reactions. And the curves, as they're formulated, very little opportunity for capturing the details of your regional models, and they say almost nothing about how to handle cyclic loading. So in PISA, we introduced not only horizontal reactions, but 3 other forms of reaction that contribute to the monopile behavior, which are particularly important with short monopiles. These extra components of distributed side shear, base shear, and base moment. And we calibrated these to advanced finite element models, which were themselves calibrated to stress path tests done in the laboratory. This was part of the work that I supervised, which was done state of the art. And this also recognizes the cyclic loading response. So the modeling, the numerical modeling, was done at Imperial College. My colleague and actually former PhD student, Lydia Zdravkovic, now a famous professor herself. And here we used, for the clay site, we used an expanded version of clay, which had a very nonlinear small strain stiffness formulation. It recognized the effect of consolidated conditions much more precisely than the usual CAM clay or modified CAM clay. And that's really important for the stiff clays that we encounter in the North Sea. And for the sand, we used a bounding surface plasticity model, and we had strength variations in the deviatoric plane, and we had a state-dependent response in the sand. And this work was led by Lydia Zdravkovic, David Taborda, David Potts, and myself from Imperial College. And that was one of our main contributions, along with the soil testing. And the soil testing was done at Imperial College in our laboratory with advanced equipment. We had 2 sizes of stress path apparatus, very high resolution local strain measurements. We could measure pore pressures at the mid-height of our specimens. We had dual axis bender element equipment. And we also looked at anisotropy with hollow cylinder apparatus. And we could make samples even of glacial till, which contains stones and so on. And this provided all of the parameters necessary to calibrate our models. And it also gave us extensions to go further than PISA to look at things like anisotropy, cyclic behavior, and strain rate dependency. Now, let's look at the importance of modeling the right soils. In the North Sea, and actually I believe in many places around the world, we find 2 classes of soils, which I'm going to typify here by glacial boulder till, and Eocene marine London clay. And we're going to look at identical specimens in terms of depth and K0 values and very similar high OCRs. And we're going to look at their normalized stress strain and effective stress path behavior. So here we have stress strain normalized by initial mean effective stress plotted against axial strain. Now the Cowden till behaves like a critical state material and is ductile and reaches peak strength when it reaches its critical state at very large strains. The London clay, however, forms a shear band at modest strains and then reduces with a very brittle response to much lower strengths. So that's a very important difference. If we have a look at this in effective stress space now, Q P dashed, normalized by P dash naught, the Cowden till dilates as we'd expect for a critical state material, whereas the London clay bifurcates and forms a shear band. And we really need to distinguish these classes of behavior if we're going to model monopile foundations in a faithful way. We also find that the stiffness strain responses of the 2 geomaterials are very different. If we normalize by mean effective stress, the Cowden till is stiffer and more nonlinear. If we normalize by strength, they cross over at one point, but the Cowden till is definitely far more nonlinear. We can look at anisotropy, and I'm not going to deal with that tonight, but we can show that the horizontal stiffnesses are much higher than the vertical for both geomaterials, but the patterns of stiffness anisotropy and strength anisotropy are different between the Cowden and the London clay. We've done cyclic testing. We've had papers in Geotechnique on this, and we've shown how the Cowden till responds, and also we know how the London clay responds, and we've seen their rate dependency. So what difference does all of this make? Well, let's have a look at a test on a 2-meter diameter monopile, horizontal load against displacement here. In green, we have the conventional PY analysis that's there in the ISO, the API, the DNV codes. And here we can see in black the field test that we conducted on a 2-meter diameter pile. And in red, we can see the predictions made in advance, Class A predictions from our 3D modeling and stress path testing. So we have an approach now that we can design in individual wind farms with. So at the moment, for example, I'm involved in 2 major wind farms, one under construction, one under design, where we've applied this approach with site-specific advanced testing and site-specific advanced modeling. And these are multi-billion dollar wind farms at gigawatt scale. So it's entirely possible to do this. And there's further work on the cyclic loading. I'm involved in a project with our friends in China at Zhejiang University in East China, Jiaotong University, whereas my colleagues in Oxford are working with the Picasso project. The Picasso one, which doesn't involve us, involves large tests at the Cowden site and another site, combined with model testing and theoretical modeling. And the idea here is to be able to deal with cyclic modeling for both clay and sand, with pseudo-random and also regular cyclic loading. And there are new models for multi-directional cases and field tests too, I believe. And these are on very large piles, up to 2.5 meters diameter. We have other work going on ourselves with both theoretical approaches and field testing, some of which I'll mention shortly. Now, the big new challenges are to go from shallow water monopiles into jacket structures and into floating water, platforms in deeper water. Now, the first oil production platform that employed a floating construction and was anchored to the seabed was the Hutton tension egg platform. And this is now nearly 40 years ago. And I worked on this project and we instrumented these foundations with actually 30 micron resolution in the seabed. And we could see exactly what was happening with the piles at that time. And what we found was that when we compared group load on the piles with movement uplift, the conventional analysis, the PY, actually for this case, TZ analysis, but it's the same for PY2, came as shown in green. Our field observations were as shown in blue, and analyses that we made based on stress path testing conducted actually as part of my PhD, and numerical analyses run with my colleague David Potts, showed much better agreement. The standard industry rules are about 4 times too soft. And we found the same with jacket structures, such as Magnus, which at the time I think was the biggest steel structure offshore in the world. So this small strain testing from the lab, combined with nonlinear finite element analysis, gave us very nice predictions. And we've been able to apply that in the PISA project and in many other projects onshore, offshore around the world. But our friends in the offshore industry told us that wasn't really the problem. They told us that they didn't really care too much about load deformation. What really worried them was axial capacity. So in the 1980s, I set about a research program which went on for more than 15 years, where we addressed the very poor reliability of offshore axial pile design methods. And we noted that at the time, it was considered unfeasible to do full-scale tests offshore. There were some onshore tests on quite big piles, and we took part in those programs, but we went with still smaller piles, which we instrumented very carefully, and we tested these at 6 sites in the UK and France, with clays with high and low plasticity index and OCR, loose and dense sands, and covering this whole range in 3 PhDs, which I'm proud to say all won prizes for the excellent students involved. Now, the key tool here was our instrumented pile. We could measure with this instrumented pile local shear stresses and radial stresses on the pile surface and pore water pressures, and we could do this during installation, equalization, and static and cyclic loading. What we found was that there was a big missing parameter in pile design methods, and that's the relative depth of the pile tip below any point in question. It wasn't there in any of the design methods, but we introduced it, and it makes a massive difference and explains many anomalies. We came up with new pile design methods, which we call the ICP approach. We put these first in the mid-90s and updated them about a decade later. We rely critically on high-quality site investigations, with CPTU profiling in the field. In the laboratory, we measure interface shear angles and special tests. We measure OCR for clays and sensitivity, and we link the base resistance directly to cone resistance. Shaft failure, we deal with in terms of effective stress, and we have different expressions for sands and clays. In sands, it's linked principally to the cone, and in clays, it can be linked to the cone, but we normally use laboratory tests. We have a means of using the same expression to cover both closed and open-ended piles, and we note that as we load a pile to failure, changes occur in the radial effective stresses, which imply important scale effects. The dilatant term here for sands, for example, is inversely proportional to pile radius. So it can dominate the response of a small model pile, but have much less influence on a large offshore pile. And this depends as well on the roughness of the pile. Now, we've carried on checking the reliability of the design methods, and recently we did this with colleagues in China, and we gathered data from around the world, including tests in Brazil. And all of these tests met our quality indices for the pile tests and for the site investigations. And we could look at the relative reliability of a whole series of different approaches that might be used in practice. And the ideal is to get a mean between calculated measure, close to unity, and to have a COV as small as possible. And I'm happy to say that the ICP procedure is about the best one. You might argue the UWA one is comparable, or some people might say better, but they're very similar. They're derived from the same basis. Whereas the routine API method has bias and a much worse COV. So this allows us in the North Sea to tune our methods to our soils and actually have both better economy and more reliability. And this has encouraged widespread application around the world and a move towards lower L/D piles. So Shell in the North Sea applied this for all their platforms from the mid-90s onwards, and typically one can get 15 to 25% savings in the North Sea. We had instrumented pile driving data that demonstrated a good fit with the ICP approach. This is published by Shell, and Shell also showed how this approach allowed to considerable economy and allowed marginal projects to proceed that would otherwise be halted. And this approach has now been applied widely in the North Sea to big wind farms with more than 100 large turbines. However, there still remains some research questions to be answered. One of these is the impact of age, pile age, and cyclic loading. So we conducted new research at field scale in France to look at these two phenomena with industrial scale piles. The first thing we found is that tension capacity against load displacement here depended powerfully on age after driving. And again, this was unanticipated. You don't find it in the textbooks, but it's enormous and important. And this has been confirmed by work by our colleagues in Ireland and in Norway. But a worry is that this will depend on scale. And so with our colleagues in Ireland, Norway, and France, we conducted tests with 51 micropiles at 3 sites, and we showed that there is a dependency of scale and that corrosion reactions are crucially important. And we're now checking what happens at offshore scale through a project called the Page Joint Industry Project. This is now completed. We're presenting our results to the sponsors, and we hope to publish this very soon with some very interesting and new results. And we included in earlier publications checks on aging, for example, at this site in Germany on large-scale piles that we wrote up about 6 years ago now. So an important point to note here is that with big wind farms, because the foundations are so expensive, it is now becoming feasible to do full-scale tests offshore and do this economically and get economic benefits from it at particular sites. And testing that we've been involved with at full scale offshore includes cyclic loading experiments. But 20 years ago, we couldn't do that. So we went to our site in Dunkirk and we explored cyclic loading in sands, and we've done this also in clays elsewhere. Now, some colleagues told us, you won't get any cyclic loading response in sands because you won't be able to generate any pore pressures with the pile scales you have and with the cyclic loading frequencies you have. This turned out to be wrong. We could get either unstable, stable, or fully metastable responses, depending on the combinations of the number of cycles, the cyclic amplitude, and the mean load normalized by tension capacity. So despite drained pore pressures, here's an example on a 19-meter long pile where for the first few hours it was cycling quite stably, and then we could get a runaway cyclic failure with a 16% capacity loss in this case. So putting together a total of 14 tests, we could draw up a cyclic stability diagram from our field experiments that distinguished unstable regions of behavior with rapid degradation to stable regions of behavior where we could cycle, it seemed, forever without a problem, and metastable areas where a certain number of cycles caused very little damage, but large numbers of cycles would ultimately lead to failure. Now, in looking at this, there's a nice result. It's empirical. How can we understand what's going on to a local scale? Well, to do this, we've gone for model testing in the laboratory. In this case, in France, in Grenoble, we developed a miniature version of our ICP pile. We put this into a calibration chamber containing many, many instruments. It's a CPT-sized probe, and we tried to replicate the conditions in our field tests with about 40 stress sensors. And what we were able to establish is, for the first time, a good idea about the stress regime, not only on the pile surface, but in the sand mass around the pile. And this provides a benchmark for numerical modeling of the problem that is proving to be very informative. And here we had a team of postdocs, which includes a Brazilian woman, Cristina Tsua, who's at Sao Paulo, and she did excellent work, particularly on the cyclic loading. And what we could do is have a look in these experiments at the stress regime we generate by installing a pile into sand. And we express this as contours of stresses, in this case, just the radial stresses. And we showed how, when normalized by the cone resistance, they radiated away from the pile tip. This is the pile tip, H equals 0, R upon R equals 1. They radiate away with radial distance out, with vertical distance below the pile tip, and with vertical distance above the pile tip. And these contouring regimes showed us how the pile installation pre-cycles and preloads a pile shaft and conditions it to give you a much better response to cyclic loading than, for example, in a board pile. Board piles fall down under cyclic loading far more easily because they don't involve these conditioning stages. So we were able with this work to test emerging methods of analysis. We started off working with colleagues at Sydney University with an ALE technique with grain fracture modeling. We went on to do more work, which is similar, but with more advanced soil models with our colleagues in China. And we've done it with discrete element modeling at Imperial College too. So all of these techniques are showing us similar answers. We're able now to recover base capacity as a function of depth, for example, which used to be impossible to do theoretically. We can capture the grain breakage that occurs beneath the pile tip, and we can match the breakage contours that we measure experimentally with those that we get from theoretical calculations. We can also pick up the radial stresses and show how they vary with radius from the pile shaft as a function of position above the pile tip. And we found this fascinating trend that the stresses are at a maximum some distance from the pile tip rather than on the pile shaft itself. And we get this by all of these methods of analysis, and it provides us with one of the key components for the pile aging that I showed you earlier. We're able to pick up also the patterns of strain, and recently we've shown that we can match also digital image correlation experiments done at Purdue University, where they've picked up the strain fields rather than the stress fields. And we can match pretty well through these emerging numerical analyses. Now, the next big challenge is to go from closed-ended piles to open tubular piles. And there are big challenges there, but that is the next task. Coming back to cyclic loading, with our instrumented piles, we could see what happens locally on the pile shaft as we have stable or unstable cycling. In stable cycling, shear stresses locally, radial stresses locally, our instruments say, instrument readings stay in tight bunches over thousands of cycles with no movement, well within the interface failure envelope defined from interface shear tests. Under unstable conditions, despite this being dry sand, we have paths that look like liquefaction analysis. And we can see the so-called butterfly wings in the effective stress paths that are constrained by the interface shear envelopes and migrate towards the origin with a rapid collapse. In between, we have cases where there are slow drifts that we can capture over time and then try to model. How can we model this? Well, the key is to see what's happening to the radial effective stresses on the side of the pile as we cycle. And once we can capture that, we can go through to a range of techniques to try to pick up the impact on the field on piles in a wind farm. If we can locate those metastable and stable boundaries by calculation, relating the drifts in radial effective stress to the cyclic loading, then basing those on site-specific lab tests, then we can do site-specific design. These element tests have to capture those preconditioning stages that I talked about, and we can do this because, as we remember, bored piles are far more susceptible to cycling in sand than driven piles. So here are some experiments. These were conducted by one of my PhD students who now works for Ørsted. These are triaxial tests, but we can also do them in the hollow cylinder or simple shear. We've got 7 different cyclic stress ratios with the preconditioning steps applied. And for 3 of these ratios, actually the effective stresses improve, they don't decline. For 2 of them, we have rapid collapse, and to 2 more, we have metastable responses, with effective stresses dropping by maybe 20% in, let's say, 4,000 cycles here. And we found the same for Dunkirk sand and also NE34 sand, very similar responses. And with our very high resolution equipment in the laboratory, we can show that these patterns of effective stress response are matched by strain and stiffness strains. We can then go to make predictions for, in this case, our Dunkirk field experiments. And the brown envelope here shows the metastable boundaries. And it's not precisely the same as the field test, but it's pretty close to it. And we did the same for model pile tests, this time based on hollow cylinder results. But it can work either way. So we have a method that works. And we can apply this to North Sea wind farms with jacket or tripod designs. Here's one off the UK coastline, East Anglia Offshore 1, with 102 large jacket structures. And this is written up with our friends from Fugro. Here's another one offshore Germany, which we wrote up with others with 40 large tripods. So we can do this for sands and clays, and we have a good methodology that works in practice. And this wind farm has been operating now for a good number of years without any difficulties. Now, there are other soils which are harder to characterize. And one we meet in the North Sea is chalk. It's a calcareous soil. It's a calcareous silt that forms a very weak rock. And there are big problems with this because the chalk collapses under impact and it's very susceptible to cyclic damage. And chalk is found over a very large area, not always at foundation depth, but it's under France, bits of Germany, Denmark, and so on. And driving in it has caused major uncertainty for tens of big projects. So we were involved with a company called Iberdrola, a Spanish company, to do work in the German Baltic, and we helped them to design full-scale field tests out here in the German Baltic in a wind farm called Wikinger, which is German for Viking. And we carried on our own support testing at a site in the UK called St. Nicholas. And we did testing there with our ICP, and we've also done testing at full scale in the field. This is out in the German Baltic. These are full-scale piles, a full-scale offshore hammer. Here's a piling rig. There it is on the seabed. There was nobody down there on the seabed. It was completely robotically controlled, but it was cost-effective to do this testing at full scale to check how the chalk responded. And what we got from that was information that we've now published on how these piles behave at full scale. We've gone on with a program for which I'm the principal investigator called ALPACA. And tomorrow we have a new test to be done at this site on a large pile undergoing lateral loading to simulate monopile behaviour as well as jacket pile behaviour. But in this case, Oxford have joined us, but we're in the lead for this one. And we have a large group of industrial sponsors and government funding. And we've installed 42 piles with a wide range of scales, and we've used a range of pile materials too. We're doing dynamic, monotonic, and cyclic testing, axial and lateral, with a whole range of pile ages as well. And what's coming from this is data that we're modeling also through numerical analysis through an associated project called ALPHA, which is run at Imperial College. And there's a lot of advanced laboratory testing, which again, I've directed in our laboratory. We have very good data from in situ testing, showing cone resistances up at about 20 megapascals. We're getting geophysical data too. We're doing soil to steel corrosion studies, and we're looking at the role of the groundwater as being particularly important. So we had very nice wireline rotary drilling, we have block sampling, and we have a big range of in situ tests as well, plus an awful lot of laboratory testing. We have 3 papers that have just been accepted into Geotechnique that describe the laboratory testing so far, and we have 1 more paper to come. So with the chalk, we feel now that we've got new design methods that are more reliable, and they differ greatly from the conventional methods that have been used up to this point. They allow much more economic foundations, and we believe more reliable performance. Now, there are many areas around the world where wind power is now becoming important. One is Taiwan and the China coastline, where the soil conditions are very different to those in Northern Europe. They're not well represented in the pile test databases either. We have very low relative density sands with very low cone resistances. We have high silt contents in clays and sands, and we have significant mica contents. And in these regions, rather than North Sea storms, we have earthquake loading and typhoon loading. And we need also to bring the regional site investigation practice to be able to undertake similar testing to that we can do routinely in the North Sea. So developers here have choices. They can either take existing methods and be consciously conservative, or they can do large-scale representative tests offshore or onshore. And we've been involved in liaising with 2 of these studies. And here's one that was done by Ørsted. This ship came all the way from the German Baltic and this is the pile test equipment, very large scale, expensive testing, but it's really worth it. On a big wind farm, you can get your money back from this kind of testing. And it's been possible to do monotonic testing, axial and lateral, and cyclic testing too. And this is allowing checks on the design and a way forward to optimizing foundation behavior. So, looking at so-called problem soils, we've been able to look at the calcareous chalk, loose sands, silt sands, and silty sites. And we've been able in each case to improve on existing standard design rules, allow for new methods to come through that can be refined by ongoing research, and we can apply these to other cases. So, for example, we're working also in rock, offshore France, and also earlier offshore Scotland. And of course, there'll be further problem soils to consider, maybe offshore Brazil, and it'll be very interesting to see how we can apply the same principles of combining high quality lab testing, high quality numerical analysis, and field observations to do better design. So to summarize, what I've described to you this evening is a long-term program of collaborative research into driven pile axial stiffness, capacity, aging, cyclic and lateral loading, and problem soils. We've integrated advanced laboratory and field experiments with database studies, reliability, numerical analysis, full-scale monitoring and testing. We've come up with field-proven design tools for the displacement and capacity responses to a range of different moment loading, lateral loading, and axial loading styles. Now, this has been one of the components that's allowed us to bring down the wind costs in the UK by 2/3 over the last 5 years. Of course, there are other advances in turbines and in the structures and in many, many factors. But now in the UK, our CO2 emissions are half of their 1990 peak. And if we carry on developing wind farms at the rate we're doing now, we'll be able to have very much less CO2 than that. And I think the UK is aiming for net zero by 2030. So there are benefits from this research in foundations. They're probably worth about $200 million a year in the UK at the moment. And the European investment rate for offshore wind is something like 40 billion per year. And we think we can probably save maybe 3% of that through the geotechnical research that I've described this evening. So if you'd like to look into this further, you can go to my website at Imperial College. You can see our recent papers listed there. You can go to the Rankin Lecture, which was kindly mentioned earlier, which was given in 2016, but Geotechnique took a long time to publish it, but it's there now. It's a free paper. You can download that for nothing. And it's very important for me also to acknowledge the contributions of many colleagues at Imperial College and elsewhere, Cambridge in situ, Grenoble, NGI, Oxford, Sydney, Dublin, UWA, Zhejiang, and other centres. And I'd like to also acknowledge the funding we've had from sources in the UK and internationally, and the industrial co-funders too. And then finally, I'd like to thank you very much for the kind attention you've given me this evening, which has been very helpful. Thank you very much indeed. I'd be happy to take any questions.
Oh, thank you so much, Richard Jardine, for your very comprehensive and enlightening presentation and webinar. So we have seen interest for a number of spectators. So there are quite a few questions. So let's see if you can manage to do most of them, okay? So the first question, let me just have a look here, is related with numerical studies. So these studies in Brazil have shown that the jacket foundation seems to be the most technical and economical alternative on the northeast coast of Brazil, in which there is high presence of calcareous soils. So a sub-question is it possible to make the monopile feasible in regions whose subsoil has a high presence of calcareous soils?
Okay, so in the UK, we have chalk, which is our primary calcareous soil for offshore wind farms. And yes, we have monopiles and jacket pile foundations in chalk. They can be difficult. I had a paper with some colleagues from NGI where we described a case where monopiles simply sank into the seabed, and they ran to great depths. That can happen. And we've carried out analyses to understand that. And we believe that our work on the ALPACA project will make it easier to decide whether to use jacket piles or monopiles, but both have been used and are feasible. It's basically a question of water depth. If your water depth is greater than, say, 30 meters, then jacket piles seem to be necessary at the moment. But at shallower depth, we have been using monopiles.
Okay, so you take
calcareous sands, there will be, you'd have to do some similar studies to look at, we know that in calcareous sands, you can have pile runs, you can have similar problems to those in chalk. So that would have to be studied with good information on your local soils.
Okay, thank you so much. So the other question, the next question is related to the application of the PISA model. So the models obtained in the PISA study were developed based on specific sites and for certain monopile geometries. Do these constraints limit the application of the PISA model to other regions with different soils and geometries, thus requiring model calibration for those regions?
I think the answer to the question is yes. So what we do, even in the North Sea, at the moment, for example, I'm advising on one large offshore wind farm, a very big one. For that, we are doing the testing with a commercial laboratory for the small strain behavior, for the yielding behavior, for the cyclic loading behavior. And then 3D numerical modeling is being done. And from that will come the design for that field. So we regard that as applying the PISA model, but it's not just simply taking the curves, if you like, for the reaction springs from our tests at Cowden or Dunkirk. It's saying the method is to do that testing in the laboratory yourself when it's necessary. And in a big wind farm, the wind farms I'm thinking of are probably, their value is $2–3 billion. You can afford to do that testing. More of a problem than the money might be having the capability to do that testing. You need to have the laboratories set up to be able to do the high quality testing. And we're fortunate that we do have that in the UK. Some countries in the world that might be more difficult, but it's fully feasible at the moment to do that on commercial investigations. There's one earlier, Tritton Knoll, where we did that, and that's now published in the ISFOG proceedings. If you want to have a look for that, you can find it, a description of how that was done. And there are quite a few now that have been done for Ørsted, and there are publications describing the application of the principle. So I think the answer is yes, particularly if the soils are really quite different from those that we've written up and published for the North Sea, then yes, you should do your own studies.
Okay, thank you, Richard. So the next question is related to the rotation, maximum rotation.
Yeah.
So isn't the definition of the surface and ultimate limit states of the monopile based on the maximum rotation wrong, since the different types of soil can deform to a greater or lesser extent before reaching these limit states?
Absolutely true. So, for example, we saw with the London clay that it forms shear bands at an early stage, whereas, say, the Cowden till is ductile. But that's not the design constraint. The design constraint is that the towers need to be kept within, let's say, 1 degree of verticality. And that's what they want for the turbine operation. So it's determined by the turbine, the rotor, and also how they look. If you had a wind farm with looking like the Tower of Pisa, people would be very worried. They wouldn't like it. And, people would be unhappy. It'd be bad for publicity. It'd be bad for everything. People would worry. So there are limits to how much the towers are allowed to deflect. And they're not geotechnical necessarily, they're to do with the functioning of the wind farm. And so what we have to do as geotechnical engineers is make sure that we stay within those limits while recognizing the stress strain behavior of the geomaterials present.
Okay, the next, maybe you can fit one or two
I think
final
so, yeah.
questions. Yeah. So
Yeah, sure.
regarding to large turbines. So
Yeah.
these 15 megawatts wind turbines have natural frequencies close to the operational frequency. Then increasing the importance of the soil damping on the design of foundations of these structures. So the actual question is soil damping being considered in the design at present under these conditions?
I think the answer is yes, but historically this has been incredibly crude. If you go to the API DNV rules, there's just a question, do you have cyclic loading, yes or no? And if you say yes, you simply use a degraded resistance model. There's nothing about the level of the loading or what it does. And this, frankly, is ridiculous because everything has cyclic loading, even if it's just from a, I don't know, seagull landing on it, there'll be some cyclic loading. So what we're trying to do is move towards more rational cyclic loading approaches. It is a bit tricky to do this. And so in the PISA project, we had what we called the damping tests, where we measured the damping experienced by the foundations under particular loading styles. And now there is the problem of reproducing that analytically. And my colleague, Felix Schroeder, and I have worked on analyses for the design of wind farms, where we've used approximate methods to do this. And our colleagues at Oxford have tackled it through, if you like, macro elements with various dashpots and springs and so on. So a variety of different approaches to doing this. I think at the moment there isn't a universally acknowledged way of doing it. And I think some of the major developers, such as Ørsted, are very keen on investing in this area now to come up with, if you like, a commercial advantage from having better ways of being able to deal with damping and cyclic loading effects. So I think this is one of the big areas that's currently under investigation and development. And certainly in our testing that we're doing, in fact, this week, we hope for the chalk, we'll be doing cyclic tests, lateral loading, and we've done a large number of cyclic tests, axial loading. And from those, we can characterize the damping behavior as well as the cyclic damage and the cyclic stiffness.
Okay, so actually the final question. So this comes from the, let's say, the centrifuge community in Brazil. Yeah. So it said that it's well known that physical modeling, particularly centrifuge tests, numerical modeling, and field tests have complementary roles. So why centrifuge tests were not included in the PISA project, also knowing that they are quite important to validate or benchmarking, let's say.
Well, you have a big problem with centrifuge testing if you want to model regional soils. So most people, when they do centrifuge testing, they'll test with kaolin or some standard sand. And what we've found in our field work is there are massive scale effects and there are massive effects of choosing the right geomaterial. I tried to emphasize that when I compared the London clay and the Cowden till, stress strain responses and effective stress responses and stiffness responses. So we think it's really important to model the true geomaterial behavior, and we think it's really important to model at the right scale. However, you'll remember that I showed some physical model tests from our experiments in Grenoble, where we were able to use the physical model to get a lot of instruments into the ground, which we couldn't do in the field. And that gave us some very nice insights into what was happening and gave us a benchmark for numerical analysis. So I see the role for physical testing as being in that kind of direction. And I think that in terms of going directly to design, it's really important that we look to large scale testing. And I think the wind industry has supported this by undertaking these very large tests in Taiwan recently and very large tests in the German Baltic too. If you had centrifuge results in Kaelin and you wanted to design a 3 billion wind farm, you'd have to ask, do I really believe this? How lucky do I feel? As
Okay.
I would say. How lucky do I feel? And you'd have to be very lucky for it to work.
Okay.
We know big scale effects, very big scale effects.
Okay. Thank you so much. So this is the last question. I'd like to pass the word now to Thiago. So that if Thiago has any question, any notes to finalize the webinar. So I don't see Thiago around, so
no,
maybe I would have to end the webinar myself. So I'd like again to acknowledge Jardine to find the time to give us this very interesting and enlightening webinar on a new topic in Brazilian standard, let's say, the fact that we don't have yet a single wind farm offshore, which is the main point here. But there are some good projects that will be inaugurated or started in a couple of years at the most. So thank you so much and for your time again. Thiago?
Very welcome. It's a great pleasure. I've enjoyed coming to Brazil a couple of times historically. It's been lovely to see my Brazilian friends, and I'm very pleased to be able to give this talk to your society. And yes, I wish you every success in developing your offshore wind. As I say, in Northern Europe now, this is going ahead at a tremendous pace with something like 40 billion a year development at the moment.
Agradeço ao professor Márcio Almeida pela excelente moderação, agradeço ao professor Richard Jardine pela magnífica palestra, e os últimos meses foram de muitas palestras no canal. Aqui falamos de todos os temas de ponta no cenário geotécnico, tanto nacional quanto internacional, e para encerrar o ano com chave de ouro, o professor Richard Jardine fez aí um trabalho muito bom, muito importante, que engrandece a nossa geotecnia. E uma palestra vinda diretamente da Imperial College certamente dá mais força para o nosso canal. O Jardine escalou todos os degraus do mundo acadêmico, mas eu posso falar para vocês tranquilamente que, como ser humano, ele foi muito acessível, respeitoso e cordial a aceitar o nosso convite, e eu agradeço muito. E que todos possam, então, desfrutar de um final de ano com muita saúde, paz. Desejo, em nome do canal e grupo Geotecnia Brasil, um Feliz Natal e um próspero Ano Novo. Nos vemos em 2022. Abração, pessoal.